Welcome to The Explainer. Today, we're unpacking the absolutely fascinating microscopic drama of organic chemistry. If you've ever wondered how tiny molecular structures actually dictate the world around us, well, you're in exactly the right place. We're looking at a specific chapter of chemistry that is literally packed with action, interactions, and the vital concepts that shape our physical reality. So, think about this for a second. What do the sweet scent of perfumes, the sharp tang of nail polish remover, and the sour bite of vinegar actually have in common? I mean, on the surface, absolutely nothing, right? But down at the molecular level, these real-world sensory experiences are all powered by exactly the same thing: oxygen meeting carbon. It's this incredibly fundamental chemical relationship that shapes our daily lives.
Okay, let's dive right into this. First up, we'll meet the carbonyl family. Then, we'll move into creating and reacting. Third, we'll hit the chemistry lab tests. And finally, we'll wrap up by uncovering their real-world superpowers.
All right, part one, meet the carbonyl family. Because chemistry, at its core, is really all about relationships and how these tiny atoms interact with one another.
Say hello to the carbonyl group. This is a carbon atom double bonded to an oxygen atom. It's sp2 hybridized and trigonal planar, which basically means it sits completely flat. But you know, the absolutely crucial word here is polar. See, oxygen is a total electron hog. It strongly attracts those shared electrons, physically pulling them away from the carbon. This makes the carbon atom electrophilic, meaning it is just incredibly hungry for electrons, and that turns this bond into the highly reactive center of the entire family.
And this brilliantly illustrates the structural difference between the first two members of our family. Just look at the aldehyde on the left. Its carbonyl group is at the terminal position, so the very end of the chain, and it's capped by a hydrogen atom. Now look at the ketone on the right. Its carbonyl group is internal, literally sandwiched right between two carbon groups. And you know what? That one simple shift in position changes absolutely everything about how these molecules behave.
But of course, to talk about them, we gotta know how to name them. This is your quick reference guide for IUPAC naming rules. Just notice the suffix swaps here. If you have an alkane, you drop the E. So for an aldehyde, like HCHO, you add -al to get methanal. For a ketone, like CH3COCH3, you add 1 to get propanone. And for a carboxylic acid, it becomes oic acid, giving us methanoic acid. Definitely keep these suffix swaps in mind, guys. They are the secret decoder ring for literally everything we're about to discuss.
Moving on to Section 2, creating and reacting. Let's actually look at their behavior in the lab when things start to heat up.
Let's see how this builds upon what we might already know about alcohols. Check out this comparison. Alcohols, they have a pretty mild smell and weak acidity. But carboxylic acids, man, they have a sour taste, a really sharp smell, and much stronger acidity. And why is that? It's because carboxylic acids exist as dimers. They form these strong intermolecular hydrogen bonds with each other. Plus, when they do release a proton, the resulting ion is stabilized by resonance. This whole setup gives them significantly higher boiling points and, of course, that distinctive sour bite.
So how do aldehydes and ketones actually react? Well, they rely heavily on a mechanism called nucleophilic addition. Let's break this seemingly complex mechanism down into an easy 1, 2, 3 punch. Step 1. A nucleophile, which is just an electron-rich species, attacks that electrophilic, electron-hungry carbonyl carbon we talked about a minute ago. Step 2. This attack creates a temporary intermediate state. And step 3, protonation occurs, which usually means adding a hydrogen to finish the reaction off. So it's just 1, 2, 3. Attack, intermediate, protonation.
So the crucial point here is understanding which of these molecules is actually more eager to jump into that 1, 2, 3 reaction. It turns out, aldehydes are significantly more reactive than ketones. Imagine trying to park a car in a tight spot. An aldehyde basically has less steric hindrance, meaning it's physically way less crowded around that reactive carbon, making it a much easier target for an attack. On the flip side, ketones have two bulky alkyl groups that are actively pushing electrons toward the carbon. That makes it less electrophilic and honestly just a lot less desperate for a reaction.
Okay, Section 3, the chemistry lab tests. Identifying compounds. I mean, we know the theory now, but if you're actually standing at a lab bench, how do you apply this knowledge? Picture this. You've got 3 flasks sitting on a table. They all contain clear, entirely colorless liquids. One is an aldehyde, one's a ketone, and one's a carboxylic acid. How do you, as a chemist, tell these virtually invisible compounds apart? Well, we do it by exploiting those exact differences in reactivity we just went over.
using specific, highly colorful chemical reactions.
Now here is a fantastic mental shortcut to remember this for your exams. If you want to identify an aldehyde, just remember the letters TFS, Tollens, Fehling, and Schiff. Just stack this memory trick visually in your mind right now. It's your mental checklist. Because aldehydes are eager to react and super easy to oxidize, they will easily pass these 3 tests, whereas those stubborn ketones, yeah, they generally won't.
Let's rapidly fire through what these tests actually look like in the lab. For Tollens' test, an aldehyde is going to oxidize and leave this beautiful, brilliant silver mirror right on the inside of the test tube. It's really cool. For Fehling's test, an aldehyde produces a really striking red precipitate. Ketones, they completely fail both of these. However, if you specifically have a methyl ketone, you can use the iodoform test, and that yields a highly visible yellow precipitate. Honestly, visualizing these bright colors is the absolute easiest way to lock these tests into your memory. And finally, Section 4, Real-World Superpowers. Let's look at some practical applications and bring all this microscopic chemistry right back into our macroscopic world.
So, we gave you TFS for aldehydes. Now, here is your second mental checklist, this time for carboxylic acid reactions. I want you to remember the word MABE. M-A-B-E. They react with metals to release hydrogen. They react with alkalis, they react with bases, and they undergo esterification. Seriously, write MABE down. Having this checklist makes it incredibly easy to recall the primary reaction pathways for carboxylic acids.
Now, what's really interesting about this is that last E in MAVE, esterification. When you combine a sour carboxylic acid with an alcohol and throw in some concentrated sulfuric acid as a catalyst, they react to form an ester and water. Now, why does this actually matter to you? Well, because esters produce incredible, sweet, fruity smells. This exact reaction is literally the chemical secret behind the artificial flavorings in your favorite candy and the super expensive perfumes sitting on your shelf.
As we start to wrap up, let's consolidate the absolute most important exam-oriented takeaways into a single, highly concentrated review. Take a mental snapshot right here. Aldehyde oxidation? Easy. Ketone oxidation? Difficult. Why are carboxylic acids acidic? Resonance stabilization. And if you need to create a brand new carbon-carbon bond, you are looking for an aldol condensation reaction. Just these 4 points alone unlock a massive portion of how organic chemistry actually operates. We've covered a ton of ground today, from nomenclature and trigonal planar geometries all the way to silver mirrors and fruity esters. But I want to leave you with this final thought. How does a single oxygen double bond shape so much of the physical world around you? The next time you smell a flower, use nail polish remover, or even just taste some vinegar, remember the microscopic drama of the carbonyl group that is making it all happen. Keep exploring, keep questioning, and I'll see you in the next explainer.